So this is part 2 of my talk on whole finiteness obstruction for DG categories. So the plan for today will be the following. So first I will recall the main theorem which I mentioned yesterday. So yesterday I was talking about its applications, but now I will sketch, briefly explain how it is proved with the main ideas. And I will also formulate its relative version, where, as I mentioned, instead of a category with exceptional collection, we have a semi-orthogonal gluing of several copies of some category. And then, if I will still have time, I will very briefly sketch the version for algebras over colored DG operands. I recall that for small DG category, for simplicity, I put K0 of A to be K0 of the category of perfect complexes over A. So the theorem is that for a small DG category, we have the following 3 equivalent statements. So first is that A is Morita equivalent to a finite cell DG category. Then second is that A is homotopically finite and the class of the diagonal is generated by this tensor products of left and right perfect A modules. And the third is that A is equivalent to a DG quotient of a category with proper DG category with a full exceptional collection, finite exceptional collection, of course, by some subcategory generated by a single object. Okay, so now it will get a bit technical, but I hope it will be understandable. So I will not go too much into technical details. But the notion which we need here, kind of fundamental, the deformed tensor algebra of bimodule. Just take any small DG category, you can safely assume that it has finitely many objects. And take some bimodule. Then the tensor algebra is just a DG category with the same objects, and the morphisms are given by the direct sum of powers of this bimodule. If there is only one object, so if this is just a DG algebra, then this is just the usual tensor algebra of a bimodule, so just the direct sum of tensor products. And this is just a straightforward version, straightforward generalization for a DG category. So it has the same object as D. And then we have a deformed version of this construction. So if we have any morphism of, of course, closed morphism of degree 1 from M to the diagonal, then we can deform the differential. So this as a graded K-linear category, we have the same category as this tensor algebra, but now this deformed differential, we can define it on the generators, and on the category D, it's just the old differential, nothing changes. And for this bimodule, we just take the old differential plus alpha. So alpha goes from M to D. It's much simpler than this general Maurer-Cattan equation. So it's just given by a morphism of bimodules. And of course we extend to the tensor powers of M by the Leibniz rule. And this construction is not invariant under quasi-isomorphisms if we don't put some assumptions on the bimodule. But we will actually apply it only to the cases when it is cofibrant on one side. And then the construction will be, of course, invariant under quasi-isomorphisms. So we have some quasi-isomorphisms of bimodules from M prime to M. And we have any morphism from M to the diagonal of degree 1. Then we have natural DG functor, which is just identity on object, and which is quasi-equivalence. And also, if we have Morita equivalence of DG categories, and we have some cofibrant, for simplicity, just assume that M is cofibrant over D. a bimodule, and we have some morphism to the diagonal. Then we can extend the scalars using this functor from D to D prime. And from this extended, I mean, after the extension of scalars, we still have a natural morphism to the diagonal, and we have a natural functor, and this is Morita equivalence. All of this is quite easy to check. You just have natural filtration by tensor powers, and you just pass to the quotients. Okay, so this is deformed tensor algebra, which we'll use systematically. Now, the example of this is the construction of Drinfeld of DG quotient. So this is just a special case. If D is a small DG category and we have some object, and so we have representable DG model shifted by 1, representable by the pair x opposite, so just the product of the representable model and its dual shifted by 1. So the identity morphism of x gives a map from M to the diagonal shifted by 1 by Ioneda lemma. And then we have literally an isomorphism of DG categories. So this deformed tensor algebra is literally the same as Drinfeld DG quotient construction of D by the subcategory with a single object x. And the same construction works. I mean, the same actually isomorphism of categories of DG categories works for an arbitrary full DG subcategory. So instead of just one representable model shifted by 1, we take the direct sum over all objects of S. What this construction does is basically it just adjoins the conjective homotopies of the identity morphisms of objects of S. Okay, this is Drinfeld quotient, and another example which we need is that if we take a finite cell DG category, so remember it's a path category of a finite graded quiver where the arrows are ordered, and we have the standard condition on the differential of each arrow can be expressed in terms of the previous arrows. If you have any semi-free finitely generated bimodule over C tangent C opposite, then just any morphism to the diagonal is twisted by 1. So if we take the deformed tensor algebra, it is still a finite cell DG category. It's quite easy to check. So what happens is basically this deformed tensor algebra is obtained from C by consecutively adding new morphisms without relations, and with this standard assumptions, standard conditions on the differential. So this is everything is ordered here. Another way to say the same thing is just to say that this functor defined composition of push-outs of generating collaborations, which I mentioned yesterday. Okay, so now the implication, probably one of the easiest implication, that 3 implies 1. So if we have this quotient of a category with a full exception collection by a subcategory generated by a single object, then we can replace this E by a directed DG category. So just take the full subcategory formed by this exceptional objects and just modify homes slightly. So we get this directed DG category. There are no homes from right to the left, and all of them are exceptional in the DG sense. And we can, in fact, assume that this E prime is a finite cell DG category itself. For example, you can just take minimal infinity module for this category and just take bar-to-bar construction. You will get exactly path category of some directed quiver. So this is we can assume that this E prime is a finite cell DG category, and now we can take some semi-free finitely generated module over E prime, which generates, which corresponds to the generator of the subcategory S. And then this, by what we already discussed, if we take this deformed tensor algebra of M tensor M dual shifted by 1, where the deformation is given by identity M, then this deformed tensor algebra will be Morita equivalent to this Drinfeld quotient of E by S. And this tensor algebra is a finite cell DG category because E prime is, and this guy M tensor M dual is semi-free finitely generated bimodule. Okay, this is probably one of the simplest implications in the theorem. Now we want to do a reverse implication. So we want to know that we want to show that if the DG category is finite cell, then it is Morita equivalent to a quotient of a category with a full acceptance collection by some single object. So we need to look a little bit at the general situation where we have some small DG category and we're just adding a new morphism. So more precisely, we have some old morphism which is closed of degree n, and we are adding a new morphism of degree n minus 1, for which the differential equals u. So equivalently, this is just again the deformed tensor algebra of this representable bimodule, the product of hx and hy dual shifted by 1 minus n. And this category where we added a new morphism, it can be actually expressed in terms of gluings and quotients. So we take the semi-orthogonal gluing of two copies of A using this bimodule, which is just the cone of this map from this representable guy to the diagonal. Then for any object of A, we have, so if iota 1 and iota 2 are the natural occlusions of the semi-orthogonal components, we have natural morphisms from iota 1 of Z to iota 2 of Z for any object of A, corresponding to identity which lives in the diagonal bimodule, and diagonal bimodule lives submodule of this cone, sub-bimodule. And then after we take this gluing, we just need to mod out by the cones of this morphisms WZ, where Z runs through any generating set of objects of A. And now, if we have a finite cell DG category, so it is freely generated by a collection, so it has finitely many objects and freely generated by the collection of morphisms, with this assumption on the differentials, then we can just proceed inductively. We can take the chain of non-full DG subcategories where Ci is generated. So they have the same objects, just finitely many objects, and Ci is generated by F1, etc., Fi. And then, by what we already discussed, we can inductively construct this localization functors, EI to CI, where EI is as a graded category, is a path category of a finite directed graded quiver. So we have a quotient functor up to direct summons, and the kernel is generated by a single object. And technical assumption that this map on objects is surjective. It is just needed for, to be able to lift bimodules from CI to EI. Yeah, so this is kind of straightforward. Straightforward corollary of what we already discussed. So this category En will be what's called smooth categorical compactification of C. So in this way, we represent C as a quotient of E modulo a subcategory generated by a single object. And this actually, this equivalence between 1 and 3, it was known for quite some time to some people. I think it wasn't published anywhere, but I think I knew it already in 2012, and probably Maxim Kontsevich knew it even earlier than that. And in the most straightforward construction of this compactification, we have this doublings. So the number of objects is 2 to the I times the number of objects of C. And the basic example, yeah, and often, of course, you can do it much more economically. So it's just if you do it in the most straightforward way, you get this doublings. Just the basic example of this is if you take just the free algebra on n generators of degree 0, then you can take the generalized canonical quiver with n+1 arrows. Also, everything is in degree 0. And then the perfect complexes over this free algebra is the quotient. This perfect complexes over this canonical quiver modeled out by the cone of U0. So you just invert this arrow U0 and you get a free algebra. This is quite easy to check. So we have basically xi equals ui U0 inverse. And of course, the special case of this is n equals 1. And then we have just a fine line on the left, and we have P1 modeled out by the skyscraper at infinity on the right. Okay, so this was equivalence between 1 and 3. Now another easy implication is, for example, that 3 implies 2. Also, 1 implies 2 is also easy to check. So, so if you take this quotient of a proper DG category with a full exceptional collection by a single object. So we already know that this A is finite cell. So in particular, it's homotopically finite. So, but we also need to show this condition on the class of the diagonal. But this actually easily follows from the fact that for a category with exceptional collection, we have this equality. Okay, isomorphism. So K0 of E tensor opposite is the same as the tensor product of K0s. And then if you, it's just a general property of this localizations in the DG setup, then that when you take these localizations, the extension of scalars of the diagonal is the diagonal. This condition on this on the diagonal bimodals, it's actually equivalent to having a localization on large categories, but in particular, if you have a usual localization on the level of compact objects, you have this isomorphism between bimodules over A. And so in particular, we see that the class of the diagonal is in the image of the composition. And we need just to know that it's in the image of the last arrow. So we see that A satisfies condition 2. So this is kind of probably the easiest of these implications. And the most interesting implication, which is remaining, is 2 implies 1. So if A is a homotopically finite DG category with this condition on the class of the diagonal, then A is Morita equivalent to a finite cell DG category. And it is proved in 2 steps. And the step 1, which was quite surprising for me, so I didn't expect this to hold, that for any homotopically finite DG category, the tensor product of A with Laurent polynomials is Morita equivalent to a finite cell DG category, to some finite cell DG category C. So in particular, you can take just any very complicated motif. I don't know, for example, even for abelian varieties, you just take any abelian varieties, you multiply it by GM, and it turns out that it's already finite cell. So it can be it can be represented as a quotient of some category with a full exceptional collection. This is step one, and yeah, there's some technical condition which is easy to handle. That for any finite collection of classes in K0, we can choose this finite cell DG category in such a way that the objects are this objects actually catch all these classes. I mean, the extension of scalars. But this condition you can safely ignore for the moment. It's kind of automatic. So the most important is this A times GM becomes a finite cell DG category. And step two, if A satisfies this condition too, so if it's not only homotopically finite, but also you have this condition on the class of the diagonal, then A is obtained from A times GM by attaching a finite number of cells. Well, I'll explain what this means, but it's basically, again, like finitely many push-outs of generating cofibrations. Yeah, and of course, up to Morita equivalence. Okay, so now I will start with step one, but before step one, I will recall a result, a topological result, which is a kind of version of step one for topological spaces. And it's a very old result by Michael Mather, 1965, that topological space X is finitely dominated if and only if X process one is has a homotopy type of finite CW complex. Yeah, well, I defined this property of being finitely dominated for CW complexes, but okay, for general topological spaces, it's just being retract of a finite CW complex in the homotopy category. Yeah, and this was known before this whole finiteness obstruction theorem, which is actually the same year, at least the year of publication, the same. But the argument doesn't use this whole finiteness, and it's very short and elegant. And we will actually generalize it to GG categories. So I will briefly explain how this is proved. Quite easy proof. So of course the if part here is obvious because X is a retract of X cross S1. So if X cross S1 is a finite CW complex, then X is finitely dominated. Okay, now the only if part is more interesting. So there is a notion of mapping torus of self-map from Z to Z. For in the topological space is just Z cross the interval, and mod out by the relation phi of X0 equivalent to X1. And this is of course the same as you can multiply by non-negative real numbers and identify pairs phi of xt and xt plus 1. So, and well, from the second description, it's immediate to see that if we take this map phi tilde from the mapping torus of phi to itself, just given by in coordinates, just phi tilde of xt goes to phi of x t. Then this map phi tilde is homotopic to identity map of this mapping torus. Then it follows that if you take any maps of topological spaces going in different directions from x to y and from y to x, then the corresponding maps between the mapping tori of GF and FG, so these two maps are homotopy inverse to each other. Just follows from what we already discussed. And in the special case, when X is a homotopy retract of Y, so if GF is homotopic to identity, then we have that this X cross S1, which is literally the mapping torus of the identity map. It is homotopy equivalent to the mapping torus of GF, and then it is homotopy equivalent to the mapping torus of FG. But now, if we also assume that Y is a finite CW complex, then this Fg is self-mapped from Y to Y, and it's easily seen from the construction that it's also a finite CW complex. So this proves the only if part. So it's a very short and elegant proof, and it turns out that it makes sense in much greater generality. We will apply it for DG categories, but before that, I will briefly comment on the more general context. So this mapping torus of any self-map can be, if phi is a map from Z to Z, can be described as a homotopy co-equalizer. So it's homotopy equivalent to, weakly homotopy equivalent to a homotopy co-equalizer of identity and phi. Well, you can also say that it's homotopy co-invariance of the monoid of natural numbers. So phi defines an action of natural numbers on Z. This is just homotopy co-invariance of this action. Now, if we take any two maps in different directions from x to y and from y to x, then this homotopy equivalences between mapping tori then can be expressed as follows. So we have this two co-equalizers, and we also have this limit, homotopy co-limit of this diagram. Here, I mean that the category, we take the category with two objects freely generated by two morphisms in the opposite directions. So we have a functor from this category to topological spaces, and we take the homotopy co-limit of this functor. And we have the natural maps from the co-equalizers to this homotopy co-limit. And these maps are actually equivalences. And the same holds actually in the homotopy category of any model category. And also you can say that it holds in any infinity category if at least one of these three co-limits exists. One of them exists, then so do the other two. And you get these equivalences. And another way to say this, the corresponding functors between this between the index categories, so this three categories from which we take the functors to topological spaces. So the functors between these index categories are homotopy cofinal, which is easy to check using any of the standard criterions. And in particular, it is sufficient to know that this holds in the opposite category of topological spaces. So if you replace the co-equalizers with equalizers, homotopy co-limit with homotopy limit. So if you know this for topological spaces, then you know this for any infinity category. Okay, and now the special case, which is probably familiar to everyone, is the case of stable infinity category. You can safely assume that it's just a triangulated DG category. So if we take this it's homotopy category, which is triangulated, if we take any morphisms in the pair of morphisms in the opposite directions, then we have this isomorphism between cones. So cone of identity of x minus gf is the same as is isomorphic to the cone of this matrix, and it's isomorphic to the cone of this of the identity minus fg. This is basically just doing some elementary transformations with this matrix with rows and columns, this is well known. In particular, the corollary, which is also well known, is that if identity minus gf is invertible, then also identity minus fg is invertible. The special case of this also if gf is identity, so if x is a direct summand of y, which is same as retract here, then we get this, we can express this x plus x shifted by 1 as a cone of morphism of identity minus fg from y to y. And this in particular explains that this, for example, if you take any perfect complex and take its direct sum with its shift by 1, then it becomes quite isomorphic to a semi-free finitely generated module. Okay, and now we need we want to figure out what happens in the special case of DG categories, which we're interested in. So let's take first any DG category and some end functor of this category. So we want to describe this homotopy co-equalizer of identity and phi. We have this standard association of bimodule. For any functor, we associate bimodule in this usual way. Then we can take the tensor algebra of the bimodule associated to this end functor. And the restriction of scalars functor from modules over D to modules over this tensor algebra, it preserves perfect modules. This is easy to check. And for example, if D is a DG algebra, then we have just a short exact sequence of modules, and the first two of them are perfect. So this restriction of scalars is also perfect. Then this homotopy co-equalizer can be computed as a quotient, can be described as a quotient. So you take perfect complexes over this tensor algebra of this bimodule, and you mod out by restriction of scalars of D. This is quite easy to check by this standard. There are standard ways to compute this homotopy co-limits over some finite categories. In particular, if we have a pair of identity and identity, then this co-equalizer is D tensor Laurent polynomials. In this special case of more general statement that homotopy category of topological spaces is acting on the homotopy category of DG categories, on the, well, say on the Morita homotopy category of DG categories. And more generally, instead of Laurent polynomials, so he is just D multiplied by the circle, but more generally, instead of Laurent polynomials, you will have single chains on the path groupoid of the topological space. Okay, so we have this D tensor Laurent polynomials, and this equivalences between homotopy co-limits, they can be checked quite explicitly. So for any DG functors going in the opposite direction, so we have this tensor algebras of NGF and NFG and quotients of them, and they are both equivalent to the intermediate category, which is you take a disjoint union of C and D. You take the tensor algebra of the direct sum of these two bimodules associated to F and G, and then you mod out by the restriction of scalars of C and D. So if you take this tensor algebra in the middle, and if you first mod out by restriction of scalars of C, you get this tensor algebra of NGF, so tensor algebra over D. And then you mod out by restriction of D, and which happens also here. So I mean, this intermediate guy is equivalent to both of these quotient categories. In the special case, when GF is homotopic to identity, we see that this D multiplied by GM, that it is equivalent to this quotient, so perfect complex over tensor algebra of NFG, mod out by restriction of scalars of C. And in the special case, so if we now consider the case when D is homotopically finite, and we are representing it as a retract of some finite cell DG category, this because it's quite easy to construct a resolution of the diagonal, it is you easily see that it is quasi-isomorphic to a semi-free finitely generated bimodule over C. Then so is this bimodule treated to the end of functor FG. Just the standard argument. If you know something about the diagonal, you can just multiply by something. And then we can just replace this bimodule M sub FG by some semi-free finitely generated bimodule. And we get a quasi-equivalence of between this tensor algebra. So we get this tensor algebra of some semi-free finitely generated bimodule. And then, as I already explained, if we want to mod out by something, and this something is generated by a single object, so we just choose this semi-free finitely generated module over this tensor algebra. So this is finite cell. So tensor algebra of M over C, this finite cell. So we choose semi-free finitely generated by module. And as I already explained, when we mod out by this P, we just take this deformed tensor algebra. And this is again a finite cell DG category, because tensor algebra of M is a finite cell, and because P is semi-free finitely generated. So we get we obtain just mimicking the proof from topology. We obtain that this D tensored by Laurent polynomials is equivalent, Morita equivalent to a finite cell DG category. And this assertion about this classes in K0 is just straightforward. You can force this category C to contain any number of representatives of classes in K0. So this was step one. And then step two, it's basically first you make easy observation that to obtain the base field from Laurent polynomials, you just need to kill x minus 1. So you just need to add a new generator of degree minus 1, whose differential is x minus 1, which is the same as taking this deformed tensor algebra of free bimodule of rank 1. 50 by 1. And then we can just multiply this for multiplied by an arbitrary small DG category. So we get this that A can be obtained from this A cross GM, again by this deformed tensor algebra, but now we have diagonal over A tensored by this free module of rank 1, 50 by 1. But now we need to use this assumption on the diagonal bimodule on its class in K0. So by what we already know from step 1 and by Thomason, we can find some finite cell DG category C, which is Morita equivalent to this A tensor Laurent polynomials, such that the image of this diagonal extension of scalars of the I mean diagonal multiplied by this free bimodule is quasi-isomorphic to some semi-free finitely generated bimodule over C. It's just here we use this condition that we can about this finite collection of classes in K0 just apply to the finite collection which is needed to generate the diagonal bimodule by the decomposable bimodules. And then after that, it essentially finishes the proof, because then you just take this deforming morphism from M to the diagonal shifted by 1, which corresponds to this x minus 1. And we get a Morita equivalence between the finite cell DG category, deformed tensor algebra of M, and the DG category A. Which we wanted to prove that it is finite cell, and we did it by only using this assumption of being homotopically finite plus the condition on the class of the diagonal. So this just proves the main theorem. And so yesterday I formulated some application of this for phantom categories and for Barlow surfaces, for Dolgachov surfaces. and for weakened version of Lund conjecture. So now I will formulate. I will just formulate the relative version and briefly mention some application of this relative version. And it can be formulated in different ways, but just to minimize this inequalities. So we choose this minimalistic formulation. So take any homotopically finitely presented DG categories. So the second category is non-zero. I mean, not equivalent to zero. Then the following two conditions are equivalent. So the first is that the class of the diagonal of A is contained in the subgroup generated by such images under various pairs of functors. Just take any pairs of functors from B to A and from B opposite to A opposite. You get a functor from B tensor B opposite to A tensor A opposite. And you take the image on K0, you get some subgroup in this K0. And if so, the condition that the class is contained in the subgroup generated by all of these images, by all these pairs of functors. So that's condition one. And condition two is that A is Morita equivalent to a quotient of C mod S, where C is just simply the semi-orthogonal gluing of several copies of B. But of course, we require that it is smooth gluing. So I mean, basically, as Dima Orlov mentioned 2 days ago, there is this condition which guarantees that the gluing is of smooth categories is still smooth, just perfectness of the bimodule. Here we have finitely many copies, so more than 2, but still it's just some condition on these bimodules. And smooth here automatically means that C will be homotopically finite as well. So the second condition is that A is equivalent to the quotient of such smooth gluing of finite number of copies, again by some subcategory generated by a single object. And it's I could add here a third condition where everything is the same, but I just remove the assumption of being generated by a single object, because even if you have localization in the weak sense from C to A, this already guarantees the condition 1, and then you can apply the inverse implication. Yeah, so this is the relative version, and it is proved by similar arguments. Actually, just the same arguments which I already used in the proving of main theorem. Main theorem was for the case when B equals K. Basically, just n-dimensional vector spaces. Okay, so now we'll formulate some applications. It is easy to see that they follow from this theorem. So first, just let's again specialize to smooth and proper DG categories, and again B is non-zero. Then the following conditions are equivalent. So first, that the class of the diagonal is generated by the compositions from A to B and then from B to A, by the classes of these compositions. And second is A is a retract of some proper, well, here, yeah, here proper is the same as smooth actually for this smooth and proper, but properness, I mean, it's just easier to check, it's just finite dimensionality of this bimodules on the cohomological level. So A is a homotopy retract of some proper semi-orthogonal gluing of a finite number of copies of B. And the third condition is that A is quasi-equivalent to an admissible subcategory of such gluing. I mean, it's quite obvious that 3 implies 2 and that 2 implies 1. And something like 5 years ago, I think I explained in the talk in Miami, the Miami conference, that 1 implies 2. But kind of new, completely new results here that 1 and 2 implies 3, which was surprising for me. This is just follows from this relative version of the main theorem, and we have a more precise statement about retracts actually, because it looks like retract is much weaker than being an admissible subcategory in this smooth and proper context, and it is much weaker. But in fact, we can prove the following: that if A and B are again smooth and proper, B is non-zero, and if A is a homotopic retract of B, then we can actually embed A into the gluing of 4 copies of B, semi-orthogonal gluing, again proper semi-orthogonal gluing. And this is done by the arguments which I already explained. I mean, 2 of these copies are needed to compactify A tensor Laurent polynomials, A cross GM. And then we need to glue these 2 copies with the same 2 copies just to kill x minus 1, where x is a coordinate on GM. Okay, maybe 4 here is not minimal. I don't know. I just did not try to minimize it. Maybe 3 is enough. And just an observation here that we can apply this, for example, to the case, just take elliptic curve. And then, of course, E is a retract of E squared. I mean, I'm assuming, yeah, elliptic curve means in particular it has a rational point. I mean, not just a curve of genus 1, but with a rational point. Yeah, then E is a retract of E squared. So we can apply this result. And we see that the Debye of E is contained in this gluing of 4 copies of the Debye of E squared. And this seems to kill just any hope for this version of Jordan-Herder theorem for semi-orthogonal decompositions. It's because here what we have on the right is gluing of 4 indecomposable Calabi-Yau categories, and on the left we have embedding. So we have embedding of some another indecomposable Calabi-Yau categories. So you cannot even hope that indecomposable Calabi-Yau categories, if it appears in one decomposition, that it also appears in the other decomposition. So it looks like that there's no reasonable weakened version of Jordan-Herder which would hold for smooth and proper DG categories. Yeah, and now I want to mention this. Yeah, I forgot to say that also this result about a pair of smooth and proper categories and this conditions. It gives in particular criterion when smooth and proper category is geometric, but it's not completely explicit, but it just says that the only abstraction is again on the level of K0. If the diagonal bimodule is contained in the subgroup generated by all these compositions through some smooth projective varieties, then you can actually embed A into the derived category of smooth projective variety. If you also apply Orlov's theorem that gluing of several copies of geometric categories is again geometric. Yeah. Okay. So yeah. Now about compactifications. So there's smooth categorical compactification of a DG category is just representing it as a quotient of some pretriangulated smooth and proper DG category. So the kernel is generated by a single object. And existence of such compactification implies that A is homotopically finite. And it was a question of Toen if, at least in characteristic 0, any homotopically finite category admits compactification. And I've constructed recently a counterexample to this, so giving a negative answer to the question of Toen. And it is counterexample to one of the conjectures of Kontsevich, this generalized version of Hodge-to-Durham degeneration for smooth and for proper DG categories, but not simultaneously smooth and proper. So there are there were two conjectures, and I think Dima mentioned a counterexample to the conjecture for proper DG categories. This counterexample to the conjecture for smooth DG categories, it's in fact homotopically finite, And it also gives an example of a category which cannot be compactified. Yeah, and now we can obtain some criterion for existence of smooth compactification, which is again not completely explicit, but still some characterization. So so A admits a smooth categorical compactification if and only if there is a DG functor from some smooth and proper category, such that as the diagonal bimodule, the class of the diagonal is in the image on the level of K0. Here it's obvious that that 1 implies 2. Then if we have compactification, then we just take exactly this functor, and the extension of scalars of the diagonal is the diagonal, as I already mentioned. But the 2 implies 1 follows from this relative version of ball abstraction. Okay, so this is compactifications, and now finally I still have some time, so I will briefly explain what happens for algebras of DG operates. So if we just specialize, so I was talking about DG categories, but if we just take DG categories with a single object, then we have this following corollary of the same methods which we used in the proof. So for a homotopically finite DG algebra, the following conditions are equivalent. So the first one is that A is quasi-isomorphic to a finite cell DG algebra. And the second is that the class of the diagonal bimodule is integer multiple of the class of the free bimodule of rank 1. And this looks completely unnatural from the categorical point of view. I mean, it happens very rarely. But it kind of makes sense in this just algebraic operatic setup. The condition 2 here is equivalent, of course, to the condition that the bimodule of differential, its class in K0, is again an integer multiple of the free bimodule of rank 1. So the bimodule of differentials is just the kernel of multiplication from A tensor A to the diagonal. This omega A is a cotangent complex of A in the operatic framework. So consider A as an algebra with the associative operand. This is cotangent complex. And then you can just ask whether the same holds for in the more general case of just any colored DG operand with some standard assumptions. In fact it does, and I will briefly sketch how it works for the commutative algebras. So just assume that K has characteristic 0. Yeah, but by the way, the same holds for simplicial algebras even without any assumptions. Simplicial commutative algebras without any assumptions on the characteristic. Commutative finite cell DG algebras are just defined in the same way. They are free supercommutative DG algebras finitely generated with the same condition on the differentials, the generators, and homotopically finite commutative DG algebras are their homotopy retracts. So we have the cotangent complex. It can be computed by taking any cofibrant replacement, for example, semi-free replacement, and taking the naive DG model of differentials, and then extending scalars to A. Oops, yeah. And then we have finiteness obstruction theorem for commutative algebras. So the following conditions are equivalent: that if A is homotopically finite, then the condition of being quasi-isomorphic to a finite cell DG algebra is equivalent to the condition that the cotangent complex is again an integer multiple of A in K0 of A. And the implication 1 implies 2 is obvious. It can be seen explicitly. But now, if we apply the same generalization of this argument of measure, of this topological argument, if we apply the same picture with co-equalizers, we obtain that this co-equalizer of identity in itself, which is just Cauchy homology, which is symmetric algebra of one forms shifted by one, that this guy will be quasi-isomorphic to a finite cell commutative DG algebra. And then what you need to do after that is just to kill this omega A. And this exactly requires, if you want to kill it by attaching a finite number of cells, then you exactly need the condition 2. Because by Thomason, you can find this semi-free, I'm sorry, yeah, finitely generated. I mean, this bimodule M finitely generated, which corresponds to this extension of scalars of one forms over A. And then you just take the corresponding deformed symmetric algebra of M shifted by 2 over B. And because B is finite cell and this guy M is semi-free finitely generated, you again obtain that this deformed symmetric algebra is finite cell, and it is quasi-isomorphic to A. So this just sketches the proof that 2 implies 1. And in fact, the same works for arbitrary colored DG operate, and I just formulate this very briefly. I don't have much time, and I don't have much more slides actually. Well, if you take any any colored DG operate, you can think of it as a DG multi-category, small DG multi-category, and you just imposed the standard assumptions for the symmetric group actions if characteristic is positive. Then we have some freedom in choosing the generating cofibrations here, but we can choose them to be free algebra of P goes to free algebra of colon of identity, P to itself, where P is some collection of cofibrant perfect left models over this DG category of operations in one argument. So we just take this collection closed under shifts, and we include all the representable modules. And this is a collection of generating cofibrations. And this condition 2, yeah, then we have the same theorem as in the commutative setup, but the condition 2 will be of the form that this cotangent complex will be in a certain subgroup K0 of the enveloping DG category. So we have this enveloping DG category, we have cotangent complex, which is the left module, and we have this subgroup generated by extension of scalars of all these guys P, which participate in the collection of generating cofibrations. And we have just the same result as for commutative algebras with this modification. And this general formulation formally implies, in fact, the equivalence between 1 and 2 of the main theorem for DG categories, and also the relative. Okay, so I think I'll stop here.
All right. Thank you very much. Any questions?
Sasha,
Yeah.
Don't understand the last story. It was related to Hinich general results that kind of compact object and category of DG algebras of any DG operates are homotopy retracts of.
Yeah, but these are homotopy retracts, and
I see.
Yeah. This is, I mean, kind of tricky question. Yeah, when they're literally quasi-isomorphic to a finite cell.
Yes.
Algebra, yeah.
Mm-hmm.
Other questions? All right. If not, So we are done with our Moscow translation. Let's thank Sasha, and so we'll proceed at 2 p.m.
Thank
New
you.
York time. Thank you.